So today I also have your midterms. I'm going to give them to you at the end of class and tell you if you have complaints, what to do with it, and blah, blah, blah. And for today, so what I had in mind to do, I looked at your homework. It really didn't look that hard. So I'm going to explain a little about the idea of beta, what you did in class, and cap M, just a little. And then I would, if you had any questions about the homework, ask me. And also we'll do a little bit of integer programming. That's the thing that I thought might be nice to do. I like it myself. So if you have any questions about homework, just at the end ask me, and we can go over any of the questions that you think might be hard. And that's it. So let's start with the, let me find my notes. Okay. So there was, maybe, okay, let's look at it like this. You had this idea of cap M, which you taught in class, that how to price different assets, you know, stock or these things, and you found that linear function, and you talked about the expected return on something to be as a function of the return on market and a risk-free rate, and you had all that optimization model that resulted in things. So now we are looking at it from a different perspective, you know. Just we forget about all those models and assume we have some data in market, and what do they do? Okay. So what a way to look at it is, well, these data are just copied from a book. You don't need to write any of the things that I'm going to say. You just, you know, it was the data from 1926 and average till 2000, which was talking about the return on certain assets. For example, treasury bills and government bonds, corporate bonds, common stock, which was the S&P 500 index, and also small firms. So what it talked was, on this time period, the average return on T-bills were 8%, on government bond 2.7, on corporate bonds 3, on common stock 9.7, and on the small firms 13.8. So basically it was saying that, you know, looking at a long horizon, little bit slower, please. You know, we had an arrangement, you know, talking in the back, not talking in the front. So the idea is, you know, treasury bills, they don't bear any risk, and you know that was the average. If you had $1 in 1926 and had invested, how much annual it would have given this back to you. And it's something that you would expect, because, you know, you expect that, you know, corporate bonds are more risky than government bonds, or small firms are more risky than big firms. So if, you know, somebody wants to invest in them, would expect a higher return. You know, otherwise nobody would go and invest in them, because if something is more risky and has a lower return, doesn't look like a really nice investment. Now, so, and this was, you know, a general idea. And then if you look at the increments of these, you would see that government bonds on average had this much more than the treasury bills. The corporate bonds had this much more. The common stock paid off 8.9 more %, and the small firms paid 13%. I hope I copied the numbers correctly, but I think I did. So this was the, you know, these are just the increments on top of the treasury bill, which we assume is a risk-free thing. You know, nothing would go wrong with it. Now then, people started looking and saying, okay, if I have a portfolio, I have some, you know, assets, and I expect the return to be something like the average of the common stock, some index, any index that you like, then how much return should I want, you know, from these? How much return should my portfolio have to even think of it as an attractive portfolio? So they started, you know, they just looking at the historical data. So they looked at that, they realized that normally whatever is the treasury bill, whatever is the risk-free rate, you would expect your portfolio to do 8.9% more than that. Okay, so So if you want to see if right now the risk-free rate is, for example, let's say 10%, well, 10% is really high, is 1.1%, and you want to see how much return you should expect from a small firm, you would say, okay, historical data shows that they make 13% more. So if I have something which is, promising me 14.1%, it's something attractive for me. So basically, what we are assuming that there is a okay. So this one, this formula that we're talking about is talking about this case. That it's saying that if you have a market, there is a difference between the risk of market and the risk-free rate, and then forget this beta for the time being. So if you want to see that if you have a portfolio which works like the whole market, you expect it to pay you this much plus whatever the risk-free rate is right now. Okay, you can put this R prime so that it's different from that RF, because the risk-free rate at any point is different. Next year the treasury bill might be a little bit different. So the idea is assume a linear relation. I'm talking totally non-mathematical. Okay, assume a linear relation that whatever is the risk-free rate, something on top of it would be something that you expect from a portfolio from market. Now people came and looked at. So this was if you had a portfolio which was like the average of the market, moved like market, the whole market. But you normally don't have such a portfolio. So you might go and buy, I don't know, stock of Dell and Amazon, I don't know, something like that. And you look at the historical data on, for example, Amazon. And you see that, you start plotting the data and looking at data like this. We start looking at, let's think of it like this. You see that historically, if the market goes up by 1%, the average on market goes up by 1%, the stock of Amazon go up 3%. Okay? Or market goes down by 1%. These are just random numbers I'm putting in. In fact, I should have copied some real numbers, but it's not really important. So if market goes down 10%, Amazon stock goes down 30% on average. Okay? So then you would assign a number to Amazon, which we call it its beta, and we say it's equal to 3. Meaning that it's 3 times more volatile than the average market. So if some stock, like let's say oil company, which is more robust, for example, it might have a beta which is really small, meaning that let's say 0.2. Means that if market goes up by 10%, this would only change 2% its price. Or if market goes down by 10%, its value would only change again 2% go down. So it would be a less risky one because change of market wouldn't affect it that much. It doesn't change that much. But this one would be a more risky thing because if market goes up, you will make a lot of money. If market goes down, you lose a lot of money. Obviously, all these things are just, I'm talking about regression historical data. There are a lot of assumptions going on here that there are normal distribution over the prices. We are assuming that past is a good idea for future. We have a lot of assumptions going on here. So, and all those models that you saw the other time, the quadratic problem that resulted in, there are a lot of assumptions going on. So if all those things are nice, if that model is correct, we can look at historical data and then find these values, see on average how does Amazon stock change with the change in market. And if it falls on a line, then we say, okay, we have a good model. That QP model, that linear relation looks nice. Everything is good. But if you do the regression and then you see that, oops, market, for example, if this is market, then Amazon has changed like this. It's a lot, So then the points don't fall in the line. Then you say, sorry, your model is not a good model. But it seems that linear model has been a good model. People have been working with it and doing it. So then that's where this beta comes from in this formula. So basically, what this formula is saying, I just want to give you a feel about what happened in the last class. I'm not talking about any mathematical thinking. What it's saying is that it's saying we have a line. We are assuming a linear relation that there is a risk-free rate happening here, and then there's a line going up here. Okay. So basically what I'm assuming is your market is giving you, let's say, the market risk premium right now, let's say it's 10%. What does it mean? It means that what people expect on top of what the treasury bill is 10%. So if treasury bill is 1%, they expect 11% from the market. So this would be 11%. This is what people would expect. This would be 1%, the risk-free rate. Now you want to buy you want to see how much is the return that you should expect from a company which is more volatile than the market. Let's say its beta is 1.2. So you're assuming since it's more volatile, it's more risky, you expect a higher return. This linear relation says put beta equals 1.2. So this would be the risk-free rate, which is 1% plus 1% plus RF. And on top of it, if this was an asset which moved exactly like market, you would have just wanted that 11%. But since this is a more risky asset, its beta is more than 1, it would change faster if market changes a little. So you would expect more than that from the return. So basically this is just the general idea of what this formula is talking. You would see this a lot next semester in your, I think, 2-3 classes. So I'm not going to explain a lot about it because you're going to learn a lot about it. I just wanted to give you a feeling of what this guy is talking about. So in general, what it's telling you is that there's a risk-free rate, there's a return expected on market. Then you go and pick a certain company. So this beta is company specific, this is market specific, and this is just a risk-free investment. So it's saying when you want to look at the return of a company, you look at the risk-free rate. That was the part of the return that you expect because it's just you can get it without any risk from somewhere else. And then since you are investing in market, you want something more return because market is more risky than that free thing. And since you are investing in a specific company, which is even more riskier than the average market, you want more. So if you look at these things, it's saying you can write this. So what I've written there would go for this thing, common stock. If you look at the small firms, there would be more risk even involved than the average because a small firm might have, for example, a small firm might go bankrupt easier. So there would be, you can add another term here, just saying that the small firms, a little bit more we expect from it because of this, because they have liquidity problems, they cannot change they don't have enough cash available or things like that. So there are two ways of looking at this thing. One of them is that QP way, writing it down, going ahead and finding that mathematical thing. The other way is looking at historical data, trying to do a regression analysis, see if this thing holds or not. You see this thing holds, then you have a theory which backs it up to, that's nice. And then you forget about the theory, just do this, go ahead. So that was just a small, brief touch upon this thing. I just wanted to say what it means. That's all. You will see this a lot next semester. Now we go to our own business, which is integer programming. Any questions about this? You would see this in your advanced economic class a lot. So don't worry. Now, this one I have some questions which I didn't find time to type it, so I'm going to put them up later, but for the time being I'm going to read it, and if you want, just write down that question. It's not a very long question. So the first question is a capital budgeting problem. So we assume that you have 5 different investments that you have to choose from. So investment 1, 2, 3, 4, and 5. And each of them you have to invest now, time 0 right now. And you also have to invest some money in it next year, time 1. And each of them would have a value. For those of you who are familiar, it's the net present value, but you really don't need to worry about it. There's just a value associated with each of them. Now, these projects that we have, the first investment, on the first year you have to invest 11, all numbers are in, let's be generous, $1 million. Okay, $1 million. So $11 million. And in year 1 you have to invest 3. For this one it's 53 and 6, 5 and 6, 5 and 5, sorry. For this one is 5 and 1. For this one is 29 and 34. Okay, so for the first one, if you choose to undertake this project, on the first year, right now you have to invest $11 million. Next year you have to invest $3 million. And the value of it after deducting all costs, just the value, would be $13 million. This one is 16, this one is 16, this one is 14, this one is 39. So this value is after deducting cost, everything gone. And now you have also cash available, or funding, whatever you want to call it. Funding. So on the first year right now you have $40 million available, and next year you have $20 million available. Now, the question is which one of these projects you should choose to maximize your profit. And for the time being, and there's two different type of projects. We assume both cases. One type is you can either take something or not take it. So it's a 1-0 choice. You either choose this thing, you have to invest 11 and 3, done, or you can not choose it and 0. Or the other way, you can just choose half of this project. It might be some kind of investment and you can only undertake half of it. So you would invest half of these amounts and get back half of these amounts. In our mathematical terms that we discussed, one of them would refer to a binary variable, the other one would be a real variable. Now, any idea on what I should choose as my decision variables? Okay, so call it what? Xi would mean what? Okay, so it would be the amount. That's okay. Amount of, okay, let's not call it amount. Percentage of project I that you choose to invest in. Okay, this seems to be a reasonable thing. So Xi would be a number between 0 and 1. If it's 0, you choose to invest nothing. If it's 0.2, it means that you choose to invest 20% in this project. Now, the first thing that we need to write is our objective function. Okay, first let's assume that they are integer variables. So we are only discussing this case, that they are 0, 1. Basically, Xi's are binary. Or you can write it like this, doesn't matter really. So we are talking about the case that they are binary variables. Now, what would be my objective function?
Maximizing the net doesn't matter.
Good. Maximizing 13x1 plus 16x2 plus 16x3 plus 14x4 plus 39x5. Okay, so this would be your objective function. This is what you're trying to maximize. Yes?
Percentage, percentage rate.
Yeah.
Then how is it binary?
Oh, okay. Sorry. Okay, sorry. So let's say we have two interpretations for xi. One of them is the percentage, which is the case that it's real. This is the case which is only either 0% or 100%. You cannot choose 50%. Okay, let's call this case A, case B. Okay, so we are doing case B right now. Okay. Well, this would just mean that it's either 0% or 100%. This would mean it can be any percentage in between. We just, okay. Now you have to make sure that you don't spend the money that you don't have. Okay, that's a really reasonable. So your constraint would be what? Good. So this would be my first constraint, which would make sure that I'm not spending money that I don't have, basically. Okay, so it's saying that whatever you spend should be less than $40 million, whatever that you have there. Because if you choose to do, let's say, choose x1 and x3, then these two would be 1, the rest would be 0. So 11 plus 15 would be the money that you would spend, which is less than 40. So it's a feasible one. Now, I have exactly a constraint like, sorry? X4 is 5, you're right. Thank you. Somebody is looking at what I'm writing, thank you. But I'm disappointed that only one person is noticing. I expected more. Not that I did it on purpose. Okay, so this would be exactly the same constraint for the second year, because you have the money problem on the second year too. Okay, nothing really fancy. Now, the next step that you should always remember, xi's are binary. We should put it there. Okay. So this would make sure that, okay, so this would be our first problem. Maximizing our profit, given that we don't spend the money that we don't have, we just keep to our constraints, and they are binary variables. Now you can extend this problem, add different small things to it and see how they work. The first thing that you might like to add to it, which is a very reasonable thing, is that, okay, if I didn't spend my money here, I want to go and spend it here. It's like that you had the cash in your pocket, you had $40 million, but you only spent $38 million. When you go next year, you have $2 more million on top of this $20 million. So it's more realistic to add that. How would you change your model to do that? Yeah, sorry? I think you're on the right side. What do you mean by subtracting it from the second?
You add excess variable.
That's a way, but that way works too. If you just good, yeah, that's the way to do it, which is exactly what you said. Excess variable, but just two different way of looking at it. So what's the amount that I didn't spend this year? It's 40 minus that 11x1 plus 53x2. So this is the amount that I didn't spend. This is the amount that I didn't spend in this year. Now add this to the right hand side here. So this is the amount that you didn't spend, just add it here. That would make sure that if there is something left here, you have it as an extra money here. It would never be negative because that's always. Or the other way is just looking at it as a, make this plus S1 equals to 40. Then whatever is left is in S1, but then you have to make sure that S1 is greater than or equal to 0. And then here, say plus S1. This is not different from that, because if you take 40 here, if you take the rest here, S1 is equal just to the same thing which I added there. This is just a nicer way of writing it down. And if there is an interest rate happening there, then you can just multiply this guy by the interest rate. You put it in bank, you get some interest rate. So this can even take care of that thing if that money that you keep this year goes next year has some interest rate. Or if there is inflation going on and your money loses its purchasing power, you divide it by something, depending on what you like to do. So that's not something that we are really concerned with. I'm just saying that you can start changing. Now there are other things that might happen in this project. Assume that they tell you you cannot choose one and two, both of them. You have to choose only one of them. Then how would you do that in this model? And you cannot. So this solution that both 1 and 2 are chosen would be an infeasible solution.
Sum of all should be equal to 1.
Okay, that's an idea, but let's see if it works or not. So somebody suggests this, x1 plus x2 equals to 1. Does this ensure that I at most choose one of them? There is a small problem with this.
x1 into 1 minus x2.
Sorry,
There's only a constraint on these two, not all.
Yeah, I just said that I can only choose one of them, but not both of them. But this doesn't mean that. This means something else.
Constraint is only for 1 and 2, not for 1 through 5.
Sorry?
Less than equal.
Less than equal. Okay, let's see what these two mean. And what's the difference between them? So this constraint would tell me that you cannot choose 1 and 2, both of them. Remember, these are binary constraints, so they are either 0 or 1. So it's telling me that you can either choose 1 or 2 or none of them, but not both of them. But this one is telling me you have to choose one of them, but not both of them. So they have different meanings. So depending on what your problem is, this might be like, let's say you are making a building and you have to choose how the foundation is built. It's either type A or type B, but you have to have a foundation. So this is the constraint that you need. You have to choose one of them and only one of them. But this one might be you want to build a, I don't know, casino somewhere, or you want to build a hotel there. But you cannot build both of them. But you can also just leave the land empty and sell it to somebody. So this would be this one. You can either make one. So these would have different meanings. Now, it's also possible that they might tell you you can choose project 3 only if you have chosen project 2. It's a prerequisite for project 3. So, sorry?
Once again?
Okay, yeah. So it's like, assume that it's a project which is like this. I don't know. your project looks like this. Okay, so there is a sequential thing. Let's say 4, 2, 3. So if you want to go to stage 2, you do project 2, you should have done project 4 before that. It's like building a hotel. You have to have a foundation, then you have to have the walls, then you have to have the, different rooms. So if you don't have the foundation, you cannot have the walls. Now, the question is, how do you model this thing that your solution doesn't have, because now the solution can be, hypothetically, the solution might be x1, let's just say it's only this case. The solution can be x1 equals to 1, x2 equals to 1, x3 equals to 0, x4 equals to 0, x5 equals to 1. This is a feasible solution for this problem. This is a feasible solution. But this would mean, in our case, build the walls without any foundation. So you want to rule out this case. Or if you want, or looking at these two projects, only x2 and x4, there are 4 cases that might happen. 0, 0, 1, 1, 0, 1, 0, 1. So these are all the possible cases that might happen. X4 being a prerequisite for x2, it means that this one cannot happen. You cannot have x2 without having x4. But this one can happen. You can have neither of them. Or you can only do x4 but choose not to do x2. Or you can choose both of them. But this one shouldn't happen. Now, what kind of constraint would make sure that this is an infeasible case, but the rest are feasible?
x4 should be greater than x2.
Okay, yeah. So if you look at what I have just written here, this would be, unfortunately, there is no methodical way to do these things. It's just, you should look at them, come up with some relation. So if you look at this thing, in all the cases, this holds, this holds, this holds, but in this case, this doesn't hold. So if I enforce a constraint, which would say x2 is less than equal to x4, this would make sure that this one would never happen. So basically what it's doing, it's just saying x4 is a prerequisite for x2. Now, okay, so we learned 2 things. We learned if 2 projects are mutually exclusive, meaning that you can only choose one of them, use this. Or if 3 projects are mutually exclusive, it's not different from this. You just say sum of these 3 is less than equal to 1. So this would mean that you can only choose one of them. This would mean, now you can start interpreting all these different things. This would mean you must choose 2 of these 3. So depending on your type of physical constraints, you can just enforce it in your mathematical model. Now let's try to interpret something. Okay, so what do you think this would mean? Just give me an idea.
First, we should do x2 and x4 before doing it.
No. First, you should do either x2 or x4 and then do x1. Okay, so this is just saying that either x2 or x4 are prerequisite for x1. You should do one of them to be able to do x1. But you don't need to do both of them. You can do both of them. So this would not rule out x2 equals to 1, x4 equals to 1, and x1 equals to 0, 1. Doesn't matter really. So this is still a feasible one. If you want to make sure that none of these 2 are, only one of these 2 is chosen, you have to use one of these constraints too. Or you can have something like this. Let's see, what would this mean? It means that x4 is a prerequisite for x1 and x2, but these 2 at the same time are mutually exclusive. Meaning that you have to do this one to be able to do one of these 2, not both of them. It's like you have to have the foundation to either use a big room or a small room. But you cannot have both rooms at the same time, but you need the foundation. So this would mean that. So you can start playing with these guys, come up with different interpretation, putting it less than equal to 2. This would mean that you can at most choose 2 of these out of 3. You can mix them and try to come up with different relations. It's not really, sometimes it might be tricky to come up with this thing. But these 2 are the most common thing that you would see. Things being mutually exclusive, or one of them being a prerequisite for the other one. You can come up with different interpretation, different constraints, and try to model them, which some of them can be really challenging. Now, here we were using something really nice. that these guys are binary. Okay? We were thinking that, okay, why this guy worked, why, what's the first one, the most important one I would say, was this one. x1 plus x2 less than or equal to 1. Why this guy worked? Because we were sure that this is either 0, 1, this is either 0, 1. So this would make sure that one of them is definitely 0. Now assume that our projects are not binary. You can choose half of them. Okay? So you can easily choose half of 2 projects. Now this basically this guy is not there anymore. And you instead of it you have this. Okay? Doesn't look like a very big change. Our model wouldn't change at all. These things would all remain the same thing. But now if we want to model mutually exclusive things, it's a little bit different. First of all, would this work or not? Would this make sure that only one of these two guys? Why? Half and half. Yeah. For example, 1/3 and 1/3. So now 1/3 and 1/3 is a feasible solution because you can choose 1/3 of this, 1/3 of it. It's less than or equal to 1. So it would not make sure that one of them is definitely 0. There is one easy way, non-linear way to take care of it. What's it? Product. Good. So you can always put this guy there. And this would make sure that one of them is 0. But this is not what we like because it's not linear. And when it's not linear, we don't know how to solve it. So any idea how to, except for people who have seen it before, any idea? Yes. Remember, whenever there is a choice of either this or that, you need to use some binary variable somewhere. Okay, there is no way out. There is nearly no way out of it. Now, how can we use this?
We use a variable y type.
Mm-hmm.
Y1 is equal to x1.
So, just a second. So we have y1, which is binary, yes? Or no, it's not binary. Y. Okay. So we define a new variable. We call it yi, which is a binary. Okay. What?
xy is y type.
xy multiplied.
Yeah, and we can define some relationship between the y type.
Yeah, but this is non-linear. You're multiplying two variables. We want to keep it linear, but you are on the right track.
Can we just put xi over absolute value of xi?
Sorry?
We put xi over the absolute value of xi.
Oh, xi over absolute value of xi. But then when it's 0, this is not defined.
Oh, yeah.
Non-linear. And you need the binary variable. Remember, you know how to do it with binary variables. So try to relate your binary variables to non-binary variables in a way that this would happen. Okay, let me give you one hint. We can go there from there. So let's look at, assume that again we want to make sure that x1 and x2 are mutually exclusive. So let's see what are the cases that we like and what are the cases that we don't like. This one we don't like. But this one we are fine with. Or this one we are fine with. Or let's say 0, 1/2. This is fine with. So what we want is one of them to be always 0. So let's look at it this way. We want to find the upper bound in a way that upper bound for one of them is always 0. For the other one, there is no bound. It can be anything between 0 to 1. Good. So we say that x1 is less than or equal to y1.
And x2 is equal to 1 minus y1.
Good. So we even don't need y. We just y. Yeah. Good. So think of it like this. If we define a new variable, we call it y. Then we say that x1 is less than or equal to y and x2 is less than or equal to 1 minus y. What happens? So y would be either 0 or 1. Whenever y is 0, this guy would definitely be 0. This can be any number between 0 and 1. Whenever this one is 1, whenever y is 1, this one would be less than or equal to 0. Both of them have a, remember, we will, at the same time, we will always have these two constraints. That these are between 0 and 1. So then when y is 1, this would definitely be 0, but this one would be any number between 0 and 1. So this would take care of these two constraints being mutually exclusive. So if we have projects which we can choose a part of them, but we want them to be mutually exclusive, we can take care of it this way. Now, this is a good trick. There's a small problem in extended naive. We have to change it a little. Now, assume that we have 3 projects and we want them to be mutually exclusive. Then how do you do this?
Bring another binary variable.
Okay.
Like
Z.
Z.
Okay.
And then you multiply y, z.
Oh, you cannot multiply by random variables. So let me state the problem again to make sure that we are on the right track. Everybody knows what we are talking. So we said that we have 2 variables, x1 and x2, and x1, x2 are between 0, 1. We want to make sure that they are mutually exclusive. We define the variable y, which is binary, and we said x1 is less than or equal to y, x2 is less than or equal to 1 minus y, and this made sure that these 2 are never chosen at the same time. Now we have 3 variables, x1, x2, x3, and we want to make sure that these 3 are not chosen at the same time. Just a second. You know that. You don't say it. I told that to you last year. So x1 plus x2 plus x3 equals to 1, less than or equal to 1, takes care of this when they are binary. When they are binary, we know that this would make sure that only one of them is non-zero. But when they are not binary, what would make sure that this thing would happen, that only one of them is chosen? Again, you need to find an upper bound which is 1 for one of them, but is 0 for the other 2 at the same time. And obviously, there should be a binary variable or more than one binary variable defined and then related somewhere to xi. Any idea? Okay, go ahead.
Well, can you just say that they all have to be less than, like, so x1 is less than y1, x2 is less than y2,
Good.
x3 is less than y3?
So that's the way how we solve it. So we define 3 binary variables, yi. So for each of these, we define a binary variable. Then we say x1 is less than or equal to y1, x2 is less than or equal to y2, and x3 is less than or equal to y3. Remember, all y's are binary variables. Then I would say y1 plus y2 plus y3 is less than or equal to 1. So this would make sure, this is exactly like the previous case. This would make sure that only one of them would be 1. But when only one of them is 1, the upper bound for one of these guys would be 1, the other 2 would be 0. So again, you can just make this thing 2. Then this would make sure that only 2 out of 3 would be chosen. But if you make this thing equals to 2, it doesn't mean that 2 of them would definitely be chosen. Why? Because if this is equal to 2, this means, for example, these 2 would be 1, but they're less than equal. You don't know. They might be chosen, they might not be chosen. So in the binary case, if you put this thing equal to 2, this made sure that definitely 2 of them would be chosen. But in the non-binary case, if you assume that this is equal to 2, it doesn't mean anything. It might be that these guys might be chosen or not. So so if you want to make sure that definitely 2 of them are chosen, you have to model it in a different way. It's not going to be that easy. So these are just some examples, okay, of integer program modeling, of how you start playing with this. You will see a lot of these again next semester when you talk a lot about capital budgeting. Yes?
We say that this is a LP.
Yeah, these are LP.
Even if we force one variable to be equal to 0,
Well, those are not LP. Those are binary programs or integer programs. But we know how to solve them in a good way. Yeah. So, but we still want the linearity to be there. It's linear, but it's not. It's linear, but it's not real variables anymore. It's discrete optimization. It's not real optimization. So, but we don't want to lose linearity. Without linearity, a lot of things go bad. So this is one case of integer programming or binary programming. What I did here was binary, only 0, 1. Sometimes 0, 1, 2, 3, it can be integer programming. which it's used a lot in capital budgeting. That's one of its use, one of the places that they use a lot of integer programming. Now, another setting that discrete optimization might be used a lot, wow, I talked a lot, is, let me see which one I should tell you. Okay, fixed cost problems. This one is not hard, it's easier. In fact, I'm not sure if you did it in class or not, so we just go over it fast. It's not like this, it's much easier than this. Now, assume that you have 3 different products that you can choose between them. So there are product 1, 2, 3, and each of them uses raw material 4, 3, 4. Let's say this is kilogram per unit. So 1 unit of product, one would use 4 kilograms of our raw material. Work, let's say, hour per unit. So you have to work 3 hours, 2 hours, 6 hours. And then there is a fixed, and also they have a monetary cost too. So there is a fixed cost of production for each of them, fixed cost, which is only in dollar. So 200, 150, 100. And then there is a variable cost. So it's dollar per unit. It would be 6, 4, 8. And this one is CJ. It's the variable cost. Okay. I think I have missed something here. I think I need it. Yeah, there should be a price too that you sell these guys. So let's say there's a price associated to. You really don't need this. Let's just say it's 10, 12, 13. I'm not really sure about these numbers. Since I haven't written them down, it might turn out that the solution is not a sensible solution, but we really don't worry about it. We just want to model it. And then you have a constraint on the total amount of raw material that you have. You only have 160 units of kilograms of this, and you only have 150 hours of worker time. So you cannot go beyond these two. Now, so what does the fixed cost variable cost mean? It means that, bless you, the cost for, okay, I'm using two different, the same thing here. Let's call this not C, let's call it capital C. So the cost, the total cost for the product J, if you use it, would be either 0 if xj equals to 0, but it would be Cj xj plus Kj if xj is strictly positive. So this is our cost structure. Now we want to write a, sorry? It's the fixed cost and variable cost, yeah. So if you don't do anything, you wouldn't pay the fixed cost. But if you even make 1, then you have to pay the fixed cost plus variable cost, whatever it is, multiplied by the number that you produced. Now the question is to maximize your profit. So this can be a cost minimization problem too if you put a lower bound on the amount that you want to produce. But let's forget that for the time being. Now, let's see how we would model it. Well, basically by using xj, I have told you what's the decision variable that we want to use. So our decision variable would be xj, which is the amount that you produce of each of them. Now, so what would be my objective function?
10 into x1 plus 12 into x2.
Okay. No, maximize the profit.
Maximize the profit.
Yeah, we are maximizing the profit. Yeah, but you said that's the same thing. Maximize 10, what?
x1
Okay, that's correct. So 12x2 plus 13x 3. Okay, what's the cost? So this is the price. This is the revenue part. Minus the cost part.
6x1 less 200.
6x1
Less
200.
200.
Okay.
Plus 4x1 less
Okay. 4x1.
less 200.
Okay.
Less 8x3
Okay.
less 100.
Okay. Anybody sees anything wrong with what? Oh, okay. Yeah, there is a small problem right away here. That you don't know if you're going to pay these fixed costs or not because they are not for sure there. If this is positive, just a second, don't rush. I have to make sure that I have something in my mind I've memorized. I should tell it. So then, if you say it ahead of me, I would not know what to say after that. I have a sequential data retrieval method. So let's say. So if you choose x1, then you're going to pay this 200. Remember, this is our cost function. But if my x1 turns out to be 0, then I wouldn't pay this 200 unless I'd like to give my money to some people for free. I wouldn't do that. So any idea how to take care of it?
Multiplied by binary variables.
Okay, multiplied by binary variables. That sounds reasonable. Why? Because it's a decision that you either pay or you don't pay 200. There's no way you pay half of it. So it rings a bell that this is a binary variable that comes into play here. So the first, I forgot. So xi greater than or equal to 0. Now I have yi's which are binary for each I 1, 2, 3. Okay, so this is my decision variable. Now, this still has a problem, but we'll worry about that later on. Okay. Now, there is only one thing that we should remember: yi equals to 0 if you don't produce, equals to 1 if you produce. And for the time being, assume that we know a way to enforce this thing. Okay. Yeah, we will enforce it. Don't worry. We will take care of this later. First, let's write down the other constraints to get rid of them pretty fast. So we have a constraint on raw material. How would you write it?
4x1
Plus 4x2 is less than or equal to 160. And you have a constraint on hours, work hours too, which would be this. So let's get rid of these guys fast. Now let's see if this thing works for us or not. If we just put this guy there and give it to Excel, anything to solve it, the solution that you would get would look like something like this. x1 equals 10. I really don't know what you would get because I forgot my numbers. I have no idea what the result would be. 5, x3 would be 6. I don't know. And then, well, this is really not the answer, but let's not worry about it. y1 equals to 0, y2 equals to 0, y3 equals to 0. When you solve it, you will see that the y's will turn out to be 0. Why? Because there is no constraint on them, and if you put them 1, you would just lower your objective function. So definitely in the optimal solution, regardless of what these guys turn out to be, this would definitely be 0. So now you want to add some constraint here to make sure that if that xi is positive, this yi turns out to be 1. And how do you do it? In fact, I'm sure that you talked about this in class. Okay, that's a good point to start. Xi has to be less than or equal to yi. This is good with a small problem. That this would make sure that if you don't produce, this would make sure that if we put yi equal to 0, xi would definitely be 0, so we would produce nothing. But if you pay the yi equals to 1, meaning that you would pay the fixed cost, then you can only produce 1 unit, not more than that. Now, if you can take care of this, then you're fine. You saw this in class. You just multiply it by a big number. Let's say in our case a big number would be 10,000. I don't know. Yeah, in this case, 10,000 is definitely big enough because you cannot produce anything. So you just multiply yi by a big number. So we don't put a number here. We just normally write it as myi. So you put this constraint there. That you can put m, a number that if you don't produce any of the other two and you just produce that one, how much you can produce. Just a big enough number. So if you put a constraint like this guy there, this would make sure that if yi equals to 0, xi would be 0, you cannot produce anything. But if yi equals to 1, then you can produce something, and you'd better produce something because you're paying the fixed cost. And since the problem is maximization, you are sure that if yi would never be 1 unless you produce something. So this would, for example, take care of this. Now, so this is the technique to take care of fixed cost. Now, this fixed cost shows up a lot of places. This was in a production, I don't know, in a manufacturing setting. This shows up a lot of places that you want to model some kind of fixed cost that you either have to pay it or not pay it. And then there's the variable part, which you would pay proportional to. Yes?
How does that guarantee that yi is equal to 1, though, if you do produce it?
Oh, because if you want to produce xi, it means that xi has to be positive.
Right.
But for this one to be positive, yi has to be 1.
But can't it be like 0.5 or 0.5?
No, yi is binary.
Okay, so
That's the whole
it
thing.
has to be binary.
Yeah, yi has to be a binary problem. Yeah, whenever there is a choice of either this or that, you need a binary thing. So, yeah, so you will see this in a lot of settings too, that you have a part of cost is proportional, a part of cost is not proportional. I don't know, you have to make a transaction, there is a fixed transaction fee, and then there is some part which is proportional to the amount that you do the transaction. Or if you are ordering something for your inventory, there is a fixed ordering cost, which is the paperwork, regardless of how much you write. You write a number on that paper, there's a paperwork cost, and then there's the cost of how much you bought. So all these kinds of things can be modeled. Not all, some of them can be modeled with this trick. So now we know a way how to model things like, fixed costs. We know how to model things like mutually exclusive. We know how to model things, something is prerequisite for the other one. So this should give an idea to you how things in integer programming sometimes work. They normally boil down to having some idea. Somebody came up with this idea that if we put this thing there, we do this. Now we're going to look at another problem which nobody has an idea how to do it. Basically, people have idea how to do it, but their ideas are not good ideas. So okay. If any of you has done some OR before or some math or something, applied math, they might have heard of a problem called TSP. Anybody knows what it stands for? Yeah, it's a traveling salesperson. So it's a traveling salesman or traveling salesperson. So the idea is there are some cities. Okay. There are some cities, and they're connected to each other. Not necessarily all to all, but let us assume all to all. Who cares? It's not really that much of a big deal. Is this correct? Yes. So all of them are connected to each other. For our case, it's not really important. And there is a distance on these roads. So we call this D12, D23, D56. Okay, just the distances. And we assume that both ways they are equal distances. So D65 equals to D56. It's not really important. Now, our problem is there is this guy who is a salesman, who is a salesperson, who wants to go from 1 to all other and come back to 1. But he doesn't want to do it just randomly. He wants to go to every city only once. And he has to go to all cities. And he has to end up in the place that is started. So there is one way to do it. Let me use another color. So this is one way, for example. Okay, this is one way to do it. So, sorry? So the problem is you start from city 1. You want to go and visit everybody and come back, end up at 1. And you want to visit everybody only once. Okay? And so the question is, find the minimum distance route. Okay? You don't want to travel more than what you need. So you want to minimize the amount of space that you travel. Now, Anybody has any idea for what to choose as a random value, as a decision variable? Well, there is a very good candidate. So what does a route mean? It means that you have to pick some roads and say that you travel on those roads. Okay, and if you plot it, the order is obvious. You know, you cannot go first this one, this one. So it's just a question of picking some of the roads. Okay, so you pick a set of roads, and that would give you a route. So a good random variable for it would be xij, which would be either 0 or 1. It's a binary decision. And what xij is the variable which would say if you go from I to j, or the other way around, doesn't matter really, from j to I. It's not really important. Basically, it would mean that if you pick this road or you don't pick this road. Okay? Now, what would be the amount that you would travel, given that these are your decision variables? You should be able to say this one.
6.
Yeah. So, if you, for example, choose this one, you're going to pick xij multiplied by dij. Sorry, x23 multiplied by d23. So if x23 is 1, basically you would this what would be added to your objective function, the amount that you travel. If it's 0, nothing would be added. Yeah. So we are not worrying about constraints at all right now. So distance. Oh, this is just a distance. This is the distance between these two. So sigma xij dij over all routes, all roads, whatever you want to call it. Okay? Or since we have all the roads, let's put it just double summation over r over j. Okay? This would give you everything. I think you need a half here because you're counting everything 2 times. Okay? It's not really important, that half. You can just even forget about this half. It's not important. So this would be the amount that you would travel. You want to minimize this. Okay? Up to now, this is the easy part. Okay? Now, this is the easy part that, okay, you can characterize your objective function very easily. You know, this is the amount that you would pay. This is the amount that, in fact, you would spend time, assuming that time is proportional to the distance, which is not a bad assumption. Now there are some constraints that we have to add here to make sure that this route that we take, this set of xij's that would be chosen, is what we like. What do we like? We want to have a path which goes to all cities and is a connected path, is not something that, you know, you can travel, it's feasible to do it. Let's try to characterize it step by step. The first thing that we want to make sure is that you go to every city. And you go once to every city. How would you write that using these constraints?
You can request another variable saying visited or not.
Oh, no. This would make sure that, so if xij equals to 1, you are sure that I and j are visited. You don't need a new variable. These are the only variables that you need. It's much easier than adding new variables. You just want to make sure, for example, you want to make sure that you have visited city 3 and there are these ways to come to the city 3. How do you make sure that you have definitely visited this? Yeah. So let's say this is 1, 2, 4, 5, 6. So this is x13, x23, x43, and so. So you just say that summation. Well, let me write it down. So you say x13 plus x23 plus x43 plus x53 plus x63 should be what? 1. Should be exactly 1. It means that definitely one of them is 1 and definitely the others are 0. Okay? Yeah, we will take care of it, don't worry. This would make sure that you definitely come to 3. Okay? This is, let me see if I have my correct formulation here. Where did I write it? Now this is a good question. Yes. Okay. So this would make sure that you definitely come to 3. Or if I want to write it in a more concise way, I would write it like this. Sigma xij over I should be equal to 1 for each j. So what does this mean? This means that all the roads that end up to J, if you sum them, it should be equal to 1. Meaning that you definitely have to go to J. Now you want also to make sure that you leave every city that you go. So how do you write that one? The other way around. So you, instead of summing over J, you sum over J's this time. So you would make sure that, you can go and think of it a little if you wanted. It's not a really big deal. This would make sure that you would leave every city. Okay? This would make sure that you come and you leave. Now, these are all nice constraints, and their number is not too large. Everything is working fine. In fact, these are these are just, if you have n nodes, you have 6 nodes here. Then there are n of these and n of these. This looks like a very nice thing. Up to now, everything is nice. Then there's the nasty part coming in, which you don't like. If you only enforce these constraints, something like what I'm going to write now might happen. That if these are your cities, if the paths are chosen like this, obviously this is not a feasible thing. You cannot do this. But these satisfy these constraints. Meaning that you come to everything, you leave everything, and that's it. That's the only constraint that we have. You have chosen, but this is not a feasible thing. Now, does anybody have any idea to make sure that this guy doesn't happen? Basically, let's see what's the difference between this thing and this thing, the dotted one. There is a structural difference between them. It's like when there are no dotted ones, you can choose 2 different set of them, and there is no line passing between them. Okay, this one and this one. There is no line passing. These are not connected to each other. But in a feasible path, something which exists, well, let me put it like this. There is no way that you can divide them into 2 sets that you cannot cross one. You should cross one of these lines. Okay? Do you see it or not? This is the crucial idea here. So basically what I'm saying is that you cannot have 2 different connected set of cities and say, go to this for yourself, go to this for yourself, and there is no connection between these 2 different cities. There should always be a way from going from this one to this one. Is it clear or no? Yes? No? Yes? Okay, that was not a good yes. Okay. Let me draw another picture here and just make sure that. So this was our problem, and we were contrasting these 2 cases. Bless you. Okay. We wanted to make. We were saying this is a good case, this is a bad case. This shouldn't happen. We shouldn't let this happen, but we should let that one happen. And I was saying the difference is, if something like this happens, you can draw a line somewhere in your graph, whatever you want to call it, that you cross no line and some of them on the other side. But in this case, you cannot do that. Wherever you draw the line to divide 2 different things, this is going to happen. Now, let's see what this means. This means that you have to, if you divide your cities into 2 groups, one of the roads that goes between these 2 groups, at least one of these red ones, should be chosen. One of the roads that cross this line should be chosen. You should be able to go from this side to the other side. Is it clear or no? Okay. I see some no faces. So let's just, unless I see no face, I'm going to repeat it. So the red line is the line that we want to cross. And we're saying in a feasible way, you have to choose one of these black ones. Meaning that in a feasible path, there is a way from going from this set to this set. One of these black ones should be chosen. Otherwise, you might end up in a case that these guys up there, and nothing happens. So let's see how we model this thing. It's a little bit tricky, but all the crucial idea is this. All the paths that cross this red line, one head is this side, one head is on the other side. Okay? That's the only thing that is specific about this path. The other paths, both head and tail are in the one side. But these black ones, one end of them is here, the other end is at the other side. So we have to add a constraint like this. If we pick xij's, if we divide, let's call this set Q, let's call this set Q bar. Okay? Just name. I'm saying that if we divide my set in my graph into two sets, Q and Q bar, and if I pick all xij's, which one head of them is here and one head of them is here, and add all of them, it should be equal to 1. Meaning what? Meaning that I have chosen at least one. In fact, it should be equal to 2, not 1, because I have to come and go back. So this means that if I divide my set, at least 2 of the lines which are crossing this should be chosen. That's what I'm saying. So if you divide it into 2 parts, at least 2 of the lines should be chosen. And in fact, it's exactly 2 of them, but you really don't need to worry if at least or not. So that's the constraint that you have to add there. If you pick one set up, one set down, then down, and then you add them, you have to be able to do this. How do you do this? You write it as a double summation. J is in Q, I is in Q bar. Nothing really fancy. So let's see what this guy is saying. This constraint is saying that if you pick 2 arbitrary sets of nodes, at least 2 of the arcs which go between them should be chosen. And then you have to write this constraint for all Q prime, Q bar, combinations. Obviously, there are a lot of ways to divide 6 points to 2 different groups. And that's the problem with this modeling. The number of these constraints is huge, is a lot. But you have to write, if you write that for all of this, meaning that for any division of these guys, you write down this constraint, then this thing would never happen and you will find a path like this. This is called traveling salesperson problem. You really don't need to worry about it. I just wanted to give you a flavor of how things might get in in binary programming. These are all binary. So this is not even, maybe you can even, sometimes you can discuss it in non-binary things. So this is just a flavor of how these modelings go on. You have to come up with some creative idea to model something. This is one of the basic ideas to do this thing. For this problem, there are a billion ways to do it and model it. None of them solves it efficiently, but they have good methods to solve it with good things. But still, if you know what it means, it's MP hard, but it's really important for computer science. So, well, this was just what I wanted to talk about today about integer programming. And this is really way beyond what we need, just to give an idea. But the other 2 were really important things that you might see a lot. Now, any questions about the homework that you want me to give hints or? Number 7B. Oh, number 7B is really easy. You don't need to solve it by hand. I tell you, you just need to add, you know how to solve part A. It's an Excel problem. You write it down. Now add this constraint to your Excel thing. So, okay, I see your problem. To plot it, you have the problem, I guess. You have to find, let me read. Everybody, let me read it so that everybody knows what it is. It's a problem that you have I think you have 5 assets. I'm not sure. You have 5, so you have the mu for each of them and you have the covariance matrix. And first it asks you to find the efficient portfolio for the general Markovits problem and draw the efficient frontier, which you should be able to do that one pretty easy. Shouldn't that hard. To do it, worst case, just solve it for a few numbers and draw it by hand. But you should be able to draw this better than that. Then the second part says there is a constraint on the amount that you can invest. You can shorten things. You have to, I think the long positions must be at least 1.5 of the short positions. So now you write down your Markovits problem in Excel. You just add this new constraint and find the efficient portfolio for certain alphas, 10, 20, whatever you like, and plot them on the same plot that you plotted the previous one, and just connect them to each other and see how the plot changes. For the second part, it's not easy to find the analytical equation which goes there, but you can easily find, just solve 20 different Excel points with different alphas. It's just pushing the solve button 20 times. Just put different alphas, find the minimum sigma for that, and then plot it. That's all. It's not a really big problem. It's in fact easy. Yes?
Problem
1? B. Oh, that's minus 39 x1, x2. Just simplify it. It says, I think this is I forgot to ask Professor Iyengar, but just assume it's x1, x2, minus 10x1, 4x2. So just say minus 39 x1, x2. Simplify it, multiply it, and simplify it. Oh, he said that? Okay, either do this, since I myself wrote down the solution with this, but if you want, it's not a big deal. Assume there's a plus here and solve it with plus. I would put down both cases. It's right, okay. It's not a really important thing, don't worry. Just write down your interpretation and go ahead. Any other question? Yes. Sorry? Is a minimum or maximum problem, you're saying? Okay. Honestly, since I haven't solved it yet, I don't know if it's a minimum or maximum, but I think... Did it stop for the max 2? Okay, it seems that it stops for max 2. Yeah. I'm going to check it and send an email for class tonight about this one to make sure that you're... I think it was... I didn't see any problem when I was just going through it. Other questions? Okay. Now the exams. Okay. Let me just first... Okay. So, let me see what I want to say about exams. Okay, good. So we solved the exam last time, so those who were in class saw the solutions, and I think I gave some hints about what's very important for me, but that's not really important. You can have a look at it online, so it's not really important. So, yeah, okay. Obviously, everybody wants first to get the exam. Normally, when I have classes, by the midterm, I know everybody's name, but since you're a big class and it's a short time, I still don't know everybody's name. So I'm going to read everybody's name to just not let you know who I know and who I don't know. And by the way, handwritings make problem for me. I have a bad handwriting myself, but please, Mark Haddad. Jeremy Cook.
Why don't we just come up with it?
Well, I want to know everybody. That's one of the reasons. Nicholas. Francois. June Kim. Mo Lei. Chen Liang. Abhishek. Ashok Tikka. Robert. Oh, I made a mistake, sorry. Now I just realized. I forgot to add your grades and put it there. You have to add it yourself. Sorry. Jerome Gilmer. It's easy to add it. I'm going to... Jerome? Well, he's not... let me just have it. Okay. Sorry, that's my mistake. I just... I'm going to tell you how to do it. Chen Wen Huang. In fact, I put your grades on the coursework, so you can see the sum on the coursework, or you can just add it yourself there. Rajeshwari is not here. Raphael. Stephen Tong. Just give me a second, guys. Hi, I'm done with the class. I'm just giving the exam. You can just stop. This part really doesn't.